Okay. So if I'm running a program with effects, I don't want to commit to an implementation yet. So what do? Really, I want abstraction and modularity for effectful programs. So let's just break down kind of what I'm looking. And by the way, I'm still a learner, and one of the things I'm looking for is other suggestions. So if someone can tell me I'm doing it all completely wrong, that would be fantastic. So what are my goals? First one is abstraction. Rather than directly implementing my program, I want to write a specification that I later interpret or implement. So this means I can swap out implementations, test with mocks, and I can do different things. I can run my program, I can pretty print it, I can serialize it, and so on. So some different ways of perspectives you can put on this. You can say it's an interface with an implementation. You can say it's syntax with semantics. You can say it's a DSL that has model interpreters. And you can even say, think of it as, I've got a source language, I'm going to translate into a target language. Okay, and I want it to be low cost. I don't want it to run like a dog, and I don't want to impose a huge penalty on the poor programmer who has to read my code, or myself writing it. So my second goal is modularity, or mix and match. So I want my languages to be modular. I want to break up a big DSL into small components. Then I want to reassemble them and write a program using all of them. I want to extend my language with new operations. And conversely, I can, if I've got some syntax sugar, I want to reduce to a smaller core language. So I need some notion of addition of DSLs. And I need a stability property. If I write a program, then I extend my language. I want my old program to run. And I want my interpreters to be modular. So if I write interpreters for a number of different languages, then I write a program using all the languages. I want to reuse that work, not re-implement from scratch. So if you're paying attention yesterday, to Tony's talk, you realize I'm asking for the expression problem. So I'm going to look at two solutions of the expression problem. So sequencing, binding, and effects. So what does this mean? So I apologize, I'm going to preach to the choir, so bear with me. So why are we here? We're trying to write, we want to have better software, and we think we can do that through having programs that we can actually reason about. So even when our programs get complex, we can still predict in some sense what they're going to do. And how does this come about? Well, we're based on the lambda calculus. So first of all, functions are values in a very technical sense. Their meaning doesn't depend on their context. They're just kind of given, referentially transparent. And function composition obeys laws. And we can use these laws to refactor our code, and it will do the same thing. We have equational reasoning. So how do we add side effects but not lose this predictability? So Eugenio Moggi worked out you could use a type system. So we're going to wrap things with types in a polymorphic way. So, and the types will stand in for the effects that we'll do later. So if we look at a function type, we've got 3 bits. So there's 3 obvious things we can do. We've got the source, the target, and the arrow. So I can wrap the source, and that gives us a co-monad. Wrap the target, and it gives us monads. And we can change the arrow itself, and that's going to give us categories, and then arrows, an improvement on that. So if we put back the laws that we had for plain old function composition and say that they have to apply, so you may recognize the monad ones, and here we have the composition ones. This gives the laws that comonads, monads, and categories should apply. Obviously there's some additional ones for arrows. And here I've used the point-free versions of bind, co-bind, and category composition. So when we've got these laws, we can refactor safely. So we've got equational reasoning and effects. So, and just a small note, this isn't limited to side effects. So effect generally is now anything that the wrap type brings us over the raw type. So we want to reuse these. So, and I have a kind of fourth goal, which is a kind of a stretch goal. Usually the literature in this subject has a setup with a pure specification, and all the effects are on the side of the interpreters. But sometimes that's not really what I want. I want my effects in the specification. So I want my program to fail if something doesn't happen, and I want to clean up after some operation. So I want a bracket. And this needs to obey appropriate laws. So this means I can't just add it as another language because I can't, for instance, guarantee that every interpreted program will exit early in that case. So I have two solutions. Against the advice of my co-worker, I'm choosing to give you the hard one first. This is so you can motivate the simplicity of the second one. So if this is confusing at all, don't worry. The second half is much easier. So the first solution, we're going to reify. So everything will become a data type. So we're going to be following data types a la carte by Wurda. And our motto is going to be turning operations into constructors. So I think if you went to Sydney Sheck's talk yesterday, then this will all look very familiar, because he gave a recap of a Scala version that Runar Bjarnason presented in a talk called Reasonably Priced Free Monads. I still think it's too much of a cost, which is the talk. So we'll start with a simple language of console interactions, make it a data type. So I can ask, give some string prompt, and I get a string back. I can tell you something, and then I get unit back. So every operation has become a constructor. I apply a continuation passing transformation. If you know what that is, that just means we can get a functor out at the end. So we have a continuation parameter. So you ask a string, and then the continuation handles the result. You tell a string, continuation handles unit, but unit to A we can just replace with A. This is sometimes known as the UNITA embedding, and you can do it automatically. If you look up co-UNITA, that's all that is. So this is good, but we want modularity. So we saw in the keynote on the first day that you can add functors, you can multiply, you can compose. So here we're going to add. So sum of functors it's basically a dressed up version of either with another parameter. So it's either the left injection or the right injection, and it's naturally a functor. So our console type we can break up into ask and tell, and we can put them back together again. All quite easy. So we can make a monad also out of any functor using the free monad construction. And Ken gave a talk a couple of years ago on exactly how free monads work, so I highly recommend that. So what is this and how do we get one? So turns out free is basically the same thing as turning into data types. So can we do it with monad? So yes. So I've written the monad class in terms of return and join, and I'm just going to apply the same trick. So return becomes return, join becomes join, and the outer applications become the functor. And that's it. So we don't actually need the GADT here, so I've just written as a normal data type, ADT. And this is a monad anytime f is a functor. So in the workshop you can implement that. So this is the naive free monad. So there are different implementations with better performance, but we'll stick with this. So what are we claiming when we say it's a free monad? So to talk about this, I need to talk about adjunctions. So unfortunately, I need to take you down the rabbit hole into a little bit of category theory. So what are categories? There are things with objects, and there's morphisms that go between objects, so they have a source and a target. So Haskell types are an example. A morphism is just a function. Functors are a category. Morphism between functors is a natural transformation. And for our purposes, that's just a polymorphic function. Category theorists have an extra law, but because of parametricity and free theorems, that's automatically satisfied. So it's quite simple for us. Monads also form a category. So a monad is just a functor with some additional operations. So a morphism between monads is just going to be a natural transformation that preserves that structure. So if I return and then apply the transformation, that should give me a return. And if I bind and then apply the transformation, that should give you the same as doing the operation first and then binding. All makes sense. So when we talk about an interpretation of a monad, like what should that be? The natural notion is a monad morphism. And this will actually be important for making this all make sense. The reason is, if I write a program in the free monad and then I translate it, if my translation wasn't in monad morphism, I'd have no guarantee that I would still obey the monad laws. So I wouldn't be able to reason about my code anymore. So this is important. So adjunctions. So usually functors go from the Haskell category to Haskell. That's the category of Haskell types. But in generally they go from one category to another. So if we did have two categories, C and D, and two functors going in opposite directions, there's this, we say we've got an adjunction when we have this kind of cancellation property in a sense. So what are we saying here? So for any object C and D, so LC lives in D, so this is the set of D morphisms from LC to D. I'm saying they line up one-to-one with the C morphisms from C to RD. So there's a nice symmetry property, and we can build one out of the other. And if anyone's done much linear algebra and looked at inner product spaces, you might be able to squint and see this looks just like adjoint operators. If you replace this with the inner product of LC and D and C and RD. So there's a nice parallel there. So sometimes we have a simpler setup. So if R is an inclusion of a small category C into a big category D, then we write it as F. We say F is the free D functor on C, and FC is the free D on C. Conversely, if L is an inclusion, then we say F is the code-free functor, and sorry, we probably write G or something. G is the code-free functor, and GD is the code-free C on D. There is a kind of joke to help you remember which way this goes, but whether it's funny or not depends on your political leanings. If you associate left with freedom, then a left-wing functor is going to be a free one, and a right one, they're sometimes called fascist functors, or another word for code-free. So the important thing is we have a simple description of all the D morphisms out of FC. They just correspond to the C morphisms out of C, which is presumably simpler. So in our case, our adjunction is between the category of monads and the category of functors on Haskell, on the category of Haskell types. Where we have, so the monad morphisms from free F to M, where N is any monad, line up one-to-one with the natural transformations from F to M. And in the case that F breaks up into a sum of functors, we can do a further little trick. So here I've just applied that, the thing above. Now, because this is a sum, we can basically pattern match. So a natural transformation out of the sum to M is a natural transformation from the first factor to M, and a natural transformation from the second factor to M, and so on up to the last factor into M. So it's a tuple of natural transformations. This is kind of nice. So if I want to interpret a program written in the free monad of a sum of languages, all I have to do is interpret each language, just as a natural translation. So we have modular interpreters. We have a precise meaning for what that is and why it's going to work. So here's an example. I've got the ask and tell from before, and I've added a lookup type. You give me a key, maybe I'll give you a value. And I can write a program. So it is pretty ugly. So you notice I'm using ask, I'm using lookup, and I'm using tell. I have to wrap each one with join, because I have these two constructors, return and join. It's not a pure value, so I have to use join. And I've got a continuation argument at the end, so I've got to handle that with return in each case. And then I've got to inject into the correct factor. So ask is the left factor, so I use the left injection. Lookup is the left-hand side of the right, so I need the corresponding injections. And tell is the right-hand side of the right-hand side, so hence that. So there's a bigger problem that because of these explicit injections, we're no longer stable under change of language. As soon as I add another one, I've got to change embeddings everywhere. So this won't work, won't fly. So what do? Add a type class. And this will manage the injections for us. So F is a subtype of G if we have an injection which is a natural transformation from F to G. And I just add instances to capture composition of injections. So F injects into F injects into the sum, and so on. Now inject is polymorphic. And if I use smart constructors, like so I can ask for any free monad which contains an ask type. Now I can rewrite, and it's as nice as I'd expect. The only thing that distinguishes this from a concrete program is the type, which tells me exactly what operations I'm using. So this is kind of nice. And just a note here, I can make the type a bit more general. But here I had explicitly this free monad. Here I can say any free monad that contains ask, lookup, and tell. How do you interpret? Well, I'm using a type class again. So interpret holds a natural transformation. I can compose them. And when I go to interpret, I'm just folding over the free monad. So if I'm at the base, I just return. Otherwise, I recurse up the tree and to the leaves. And this is a monad morphism. So let's run it in this particular monad. If I give some instances, then I can run it, and it works. So how do we add effects to the specification? Now this isn't that clear what to do, because all we know about our monad, our free monad, is that it's a monad. So if I need kind of an extension, I really need an analogy for free, but with monad free instead. So the free monad free. And this would have to obey the appropriate laws, and it would have to satisfy a universal property like we saw for free. This kind of, yeah. So this is tricky. If we wanted to have base our program on co-monads instead, we could use co-free monads, but we'd have to go through the whole mechanism and create co-data types a la carte with a type class for projections, and have to compose projections. So I kind of have to reinvent the wheel. If we wanted arrows, I don't know what to do. Free arrows ought to exist, but we don't have an implementation in Haskell as far as I know. Yeah. If you want to know more about co-data and co-monads, I highly recommend David Lang's talk from last year. It's on the net. So this is very slow. So this is largely to do with our naive free monad, but we've also got these injections, and so we're going to be linear in the depth of that tree there. It's quite complex. I've got a lot of boilerplate. Particularly the last two are kind of controversial. And there's technical issues. Haskell's type solver doesn't backtrack, so it turns out we can only nest on one side of the plus when we're doing our instances for the injections. And this is a bit of a pain. There are other solutions, but they end up being fairly complex. So our second solution, we keep our operations as functions. So here, we're calling this the Tagless approach, following Oleg Kiselyov's type Tagless final interpreters. And the motto here is just let the compiler do it. So what is a language? A language is a type class parameterized by a data constructor. So the parameter is going to have a kind starter star. So here's what console looks like. Ask takes a string, returns a string. Tell takes a string, returns unit. And here's a key val type, where I've got set as well here. So give me a key, maybe I'll give you a result. Give me a key and a value, and I give you nothing back. So what's an interpreter? An interpreter is just a type, but it's got to have an instance. for your operations. So here we implement console in IO just with put strlen and getLine. Here we implement, obviously your natural instance for keyval is a map. So lookup is lookup and set is insert. And adding languages just means adding constraints. It's easy to split languages. You just break up the type class. And it's easy to put them back together again. You just tuple them. So our languages are completely modular. And our interpreters are modular, and we just add new instances to the type. If we want a monadic computation, that's just another constraint. So here's our quota example from before. It's the same as, basically the same as the other one, but we have this monad constraint, which just means we can use a do loop. So if you give me a monad that'll satisfy all these, then I can run it. Now effects on the specification side is actually easy. We just add a different constraint in place of monad. So here's a program to change your password and have a monad throw constraint. So this is from the edcommets exceptions library. So if we ask you for your name, I'll ask you for your password. If they match, then if they don't match, then I throw an exception. An exception here depends on the definition in monad throw. So this could be completely pure. It could actually throw an exception, kind of you choose. Now I ask for your password. If they don't match, I blow up. Otherwise, I change the password and let you know. So that's kind of nice. If I wanted a co-monadic operation, computation instead, and using arrows, I just add the relevant constraint. That all goes through quite nicely. Interpretation is just the identity function, which is somewhat counterintuitive, but all we're doing is choosing a type. So here I'm running that program in state t map string IO. So all I do, you notice that here there's no interpret. I just run state t on my program and chooses the type, and then I run. Okay, so kind of summing up. The a la carte approach, we had free monads over sums of functors. Interpretation was a monad morphism, which we built up in a modular way from interpretations for each component language, where we didn't have to worry about preserving the monad operations, they were just natural transformations. The tagless approach, languages were high-counted type classes. We combine languages by adding constraints. Interpretations are just types with the instances. So compared to a la carte, we've got minimal runtime overhead. We didn't need the boilerplate. Required fewer language extensions. But it's not all one-sided. If you've got an actual data structure, as you do in the a la carte approach, there are some other things you can do. You can step through instruction by instruction. You can have coroutines. It's easier to serialize, and there's some advantages there. What else can you do? So you could just stack free T, but then you have some problems with lifting. You can use better free monads. So if you went to Ken's talk yesterday, you will have met the church encoded free monad, which I think Van Lahoven wrote about. There's the reflection without remorse approach by Alek Kiselyov, where you use a more efficient data structure like a finger tree to hold your monadic computation states, so that otherwise the free monad, the naive one is quadratic in when you run, because the fmap operation is substitution at the leaves. So every time you fmap, you need to traverse right down from the root of the tree to all the leaves. You could do algebraic effects, so you don't have a monad stack at all. So this could conceivably be faster than either approach, if you believe the literature. Because in the end, I was running all of these in MTL, so I'm kind of limited by what MTL can do. So one instance of these is, again, Alek Kiselyov's freer monads and more extensible effects. It's a good read. So a lot of the literature here isn't so much about the case with binding. We just have expressions, and we want them to be extensible. So there's a much bigger literature on this, both in the a la carte approach and the tagless. So I'd highly recommend looking at the comp data package for an illustration of how this works. And for the tagless approach, yeah, there's a lot of material in type tagless final interpreters. Yeah, it's a very good read, and he shows you can do some somewhat surprising things, like how do you can pattern match in the tagless approach. Yeah, it's quite interesting. And that's all I've got. Thanks everyone.